Hi, in this video, I'll show how to solve an analysis of variance problem. We usually say ANOVA for short. I will lay out all the steps in solving ANOVA, and the technology I will use is StatCrunch. I'll have a separate video explaining the conceptual idea behind ANOVA. When that's done, I'll put the link up here and also in the description below. Make sure you subscribe to get all my contents. A quick overview of ANOVA. We use ANOVA when there's one numerical variable and we're comparing the means across 3 or more independent populations. Since there is only one variable, the test is called one-way ANOVA. In a typical first course in statistics, we don't teach two-way ANOVA. The variable is often called the response, whereas the different populations can be called different factors or sometimes different treatments. Since there are many populations at issue, you need to always define your parameters. If you use mu1, mu2, mu3, define what they are, or use subscript that are descriptive. For example, if you're comparing across ethnicities, then use mu sub Asian, mu sub Latinx, mu sub Black, mu sub White, etc. In ANOVA, the null hypothesis is always that the means are equal. And the alternative hypothesis is always that they're not all equal, meaning at least one is different. ANOVA, however, does not test for which one it is that's different. In order to get there, there are further steps to be taken after you've done the ANOVA test. Conditions for ANOVA. You must always check condition before running the ANOVA test, or for that matter, any hypothesis test. These are the 3 conditions for ANOVA. Number 1 is independence. The observations need to be independent within and between groups. For a classroom exercise, usually this is met by having a simple random sample. Second condition is normality. Sometimes a QQ plot is given, and sometimes you're given box plots that are symmetric. And the third condition is called homoscedasticity, and it means that the populations have approximately equal variability, meaning variance and standard deviation. Now, ANOVA is what's called a robust test. If you don't quite have normality, or if you don't quite have homoscedasticity, it will still work. When you run technology on ANOVA, this is a typical output where you have a lot of information here. This column GF stands for degrees of freedom. SS stands for sum of squares, and MF stands for mean squares. MS for the columns is usually called MS between because it reflects the variability between populations. The MS error is also called MS within. It reflects the variability within each population. Now, these first 3 columns are important if your professor teaches how to compute ANOVA manually, and you need all of this information to do your calculations. I don't teach that, so I'll move on to the next column, which is F-stat. F-stat is the test statistics using the F distribution. It's actually equal to the MS between divided by MS within. 1567.7293 divided by 7.58375 is 206.72218. And over here is the p-value. Because ANOVA is the right-tail test, a large f-stat gives us a small p-value and vice versa. Once you have the p-value, then you can compare with alpha and draw the conclusion. Recall that H0 says all means are equal, and HA says at least one mean is different. If p-value is less than alpha, we reject H0 and conclude HA is correct. There is sufficient evidence that at least one population mean is different. And don't forget to put in the context, such as at least one mean height across ethnicity is different, or at least one mean test score across the high schools is different. Whatever the problem is verbally about, put that in your answer. And then if p-value is not less than alpha, then we don't reject H0, and the conclusion is there's not sufficient evidence that any population mean is different. Of course, also supply the context of the problem. That was an overview. Now let's do an example. The RamenRater.com is a website that gives ratings to several thousand brands of instant noodle from all over the world. The ratings rank from 0 to 5 stars. The noodles being reviewed come in many different packaging styles, such as bowl, cups, packs, or tray. Assuming the noodles were randomly selected, test the claim that the ratings of different packagings are the same. Alpha is equal to 0.05. Box plots of the ratings for different styles of packaging are shown. First thing first, we need to figure out what kind of hypothesis test this is. Here it says to test that the mean ratings are the same. And there are at least 4 different packaging styles. So we're comparing the mean across at least 4 populations. That makes this an ANOVA test. Great. Now let's define the parameters and write the hypotheses. We're going to make the parameters understandable by using verbal subscripts that are descriptive. So mu sub bowl is the mean rating of noodles in bowls, mu sub cup for cups, etc. We haven't seen the data, so we don't know how far this goes. We don't know if it stops at 4, but you get the idea. Write the hypotheses. H0 says all means are equal, and HA says at least one mean is different. Step 2, check the conditions. There are independence, normality, homoscedasticity. Condition 1, independence? Yes. We're told the noodles are selected randomly, so there's independence both within and across populations. Condition 2, normality. Let's look at the box plots. They don't look symmetric at all. They all have outliers on the low side. So this condition is not met, but we'll go on anyway. Condition 3, homoscedasticity. Again, let's look at the box plots. The IQRs look kind of similar, even though that second box plot has no whiskers, whereas the others do. I would say close enough. And if you say that this condition is not met, I'm okay with that too. Either way, we're moving ahead. In a first semester statistics class, when you check conditions and it looks like they're not met, you should go on and finish the problem anyway. All right, now let's move on to the computation step. The technology that I will use in this video is StatCrunch. There are 3 ways the data can come in as. They can come in as raw data where there are several rows of data and the distinguishing factor is in one column and the variable is in another. This is how real-life data usually come in. StatCrunch can handle this, and so can the Casio graphing calculator, but not the TI graphing calculator. The second way that data can come in is they're already separated by different factor levels and placed in separate columns. So all the bowls in one column, all the boxes in one column, all the cups, all the packs, and all the trays. This is how the TI graphing calculator is typically set up. And the Casio, you have to do some extra work to get there, where StatCrunch deals with this pretty much automatically. And the third way that data can come in is fully summarized. There's no data, you don't see the actual star ratings, you just see the sample size, sample mean, sample standard deviation. There's no StatCrunch for this, there's no TI or Casio for this. This is the thing you use if you compute everything manually. So I'm not going to do this. I'm going to do the first 2 ways that data can come in. Let's do StatCrunch for when the data come in raw, 1 row at a time. The packaging stars in one column and the star ratings are in another column. Recall that different populations are called different treatments or factors or factor levels. And the variable that we're measuring is called the response. Keep that in mind as I switch to StatCrunch. All right, so I'm in StatCrunch and all the data are in raw format, the way they are most likely to come in if this were real life. The response variable is here under stars, and the different treatments or factor levels are here under style. Right, so I'll just run StatCrunch by clicking on Stat, and then ANOVA, and then one way. and I get this dialog box. I should click on this values in a single column because indeed the values of the response variable are all in a single column. I tell it where the response variable is. It's under star rating. And I tell it where the factors are. Those are different populations and they're under style. Here it is, style. Click compute. And I get these results, lots of information. But what I really need are down here, the F statistic and the p-value, very small p-value. Okay, now let's go back and do it for the other way that the data can come in with all these different styles separated out by columns. The ratings for bowls are all in one column, another column for boxes, cups, packs, and trays, all separated out. So here's how it appears on StatCrunch. And again, I go Stat ANOVA one way. And I get this dialog box again. And I choose all the columns where the star ratings are listed under, and that's all of them. By the way, either method, there are a bunch of other options down here. Just leave them as default. I click compute. And I get these results, same as before. Here's the F-stat, same F-stat, and same p-value. Awesome. Now that we have the results, let's write our conclusion. The p-value is here, and it's very small, less than alpha. Therefore, we reject H0, and that means HA is true. The written conclusion is there is sufficient evidence that the mean star rating of at least one packaging style is different from the others. See how I have the context here? You need to get in the habit of providing a verbal answer that includes the context of the question. In real life, your assignment was usually given like several months ago. So by the time you come back with the answer, your client or your boss has already forgotten what they asked. You need to provide context for them to understand. Anyway, so that's one way ANOVA. Hope it helps. Thanks for watching. Subscribe for more contents. Bye.